Yeah. Okay.
Okay, I'm not sure where that will save, but we can find it.
Yeah, we'll figure it out later.
Actually, Calvin, it might be better to for you to be co-host as well, so that you can record because the recording will our end then.
Okay. I'm just a guest now, so can you make me the co-host?
Uh, yeah, I think I just did.
Okay. Yeah. Okay.
So did you want me to, sorry,
Yeah, just give it like 3 more minutes or so.
you're happy with me still recording?
Yeah, yeah.
Okay.
Okay. It's 15 past the hour, so let's begin the guest lecture. Today we have Professor Ben Mosby, who's a professor at the Imperial College London. I first met Ben when I was on exchange at ETH Zurich, where he taught me scientific machine learning. And this course was very influential in my research direction, so I wanted to invite him here as a guest lecturer. With that out of the way, let's get on with the talk.
Yeah, thank you very much, Calvin, for the introduction. Um, yeah, so I'm very excited to be speaking to your workshop or lecture course on scientific machine learning. And as Calvin mentioned, this is kind of inspired by a course that we gave at ETH Zurich, which was called AI in the Sciences and Engineering. And I've got a slide or a QR code for you to look at the end of the talk, where we really try to teach all of our students kind of key concepts about scientific machine learning, physics-informed neural networks being one of those techniques. So I'm going to try and give you in the next, I guess, 40 minutes, kind of a brief overview of the field of scientific machine learning, kind of why it exists. And then I'll talk more specifically about physics-informed neural networks. And if I get time at the end, I'll give you some of the kind of state-of-the-art research that my group at Imperial is now working on towards pins. So we'll see how far we get. Um, Feel free to ask a question as I go along in the chat, and I ask Calvin to interrupt me and ask that question if it's relevant. Um, so yeah, let's just get started. So let's start really high level. I imagine you're all aware because you're part of this scientific machine learning kind of lecture series. But AI and machine learning is having a massive impact in science today, and its use in science is growing every year over the last like 5 to 10 years, I would say. And we're having some now really big breakthroughs in applying AI to big scientific problems. So I've just got some examples here how AI is affecting many different domains in science. So one example is AI affecting particle physics, and today, our large particle colliders generate huge amounts of data every day, and it's basically impossible to kind of look through all of these events that these particle colliders produce by hand. And so there's now been a lot of interest in designing kind of AI applications, and in this case, convolutional neural networks to automatically kind of go through this data and look for a kind of interesting particle events. So this was a very early example of convolutional neural networks being used for detecting particle events in accelerators. So that's in particle physics. In chemistry, I think this is a very well-known example. This is AlphaFold. So this is a really large deep neural network trained by Google DeepMind. And for the first time, they're able to kind of accurately predict the structure or the 3D structure of proteins given their amino acid sequence, so the building block sequence of the protein. And this was a task that used to take months or even longer in the lab by humans to complete, and now we can do it on seconds on a GPU. And this model has really created a whole research field in its own right of kind of accelerated computational chemistry. Now, here's another example is nuclear fusion. So nuclear fusion is kind of a really exciting uh, way to produce clean energy. And there's a lot of research really trying to make this viable commercially. And what we do in fusion is we combine particles or molecules together and collect the energy that's released. But to do that is really difficult. We have to create really extreme conditions inside of these fusion reactors, temperatures, or like similar to like what we would see in the sun. And so a key task of designing a good fusion reactor is basically to control the fusion. And so this is another paper that came out in Nature. Again, Google DeepMind, but this time with a collaboration with EPFL in Switzerland. And what they trained here was a neural network to help control the reaction inside of a real nuclear fusion reactor. And this was trained using reinforcement learning, and you can see in the results on the top left here how the network is not only able to kind of keep the fusion confined, but it also can change the kind of shape and position of the fusion profile, however the user would like. So I would say AI is really helping to accelerate kind of scientific breakthroughs or progress in fusion design. Then the final kind of example I've got is AI for climate science. Maybe a lot of people have seen this as well. These are these now famous models such as ForecastNet by NVIDIA, GraphCast by Google, and many other tech companies and academic kind of universities have models too. And these models are fundamentally changing how we think about simulating the climate rather than relying on very traditional numerical models where we put in a lot of physics and a lot of complex physics. Uh, there's kind of a new paradigm shift, which is just to use a large neural network given all of the previous observations of the climate, to try and predict the next time step of the climate. And that's kind of what these forecast net or similar models are doing, is they take kind of previous time frames or measurements of real measurements of the climate and try to predict into the future. And what's really impressive is these models are being trained at scale and are now becoming competitive, if not outperforming our traditional numerical models, with some important caveats. But there's a lot of excitement in using AI in this setting to really accelerate climate simulations. So I hope I've convinced you that AI is having a massive impact in science across different areas. And um, maybe you're aware of the Nobel Prizes that were awarded in 2024, um, both in chemistry and physics. And they both were regarding the overlap between science and AI. So um, the Nobel Prize in chemistry was awarded basically for that AlphaFold research that I showed just before. And then the Nobel Prize in Physics was kind of for foundational discoveries that enable machine learning and artificial neural networks. And it's kind of acknowledging that there is actually a really deep link between kind of physics and machine learning. And kind of, neural networks are inspired by how our brains work, kind of neurons in the brain. And so there really is this deep connection between kind of our whole world of science and the whole world of AI. So what do we care about in science, uh, and what tasks would we actually like to solve with machine learning in science? I think that's a really important kind of question to ask before you embark on kind of designing scientific machine learning algorithms or AI for science. And I would argue that the majority of kind of problems that we care about in science really boil down to understanding kind of partial differential equations. And these are, you know, the fundamental building blocks that are super effective at describing kind of many different scientific phenomena in the world around us. Uh, we can use PDEs, partial differential equations, to describe scientific phenomena at the smallest scales. So, for example, the Schrödinger equation for atoms and particles, and physics at the largest scale. So, for example, Einstein's field equations and for studying gravity and space-time. We also use PDEs to describe, Earth. So those climate simulations that I was talking about use a lot of different physics, including the Navier-Stokes equations and wave equations and uh, radiative equations. And what I find really cool is that we can also use PDEs to describe kind of biology and things that you wouldn't necessarily think would be obeyed by differential equations. And so it turns out, for example, the patterns on the skin of animals and fish, the growth of those patterns can be described by certain equations. So in this example, this is the solution of a reaction diffusion equation. Um, so it's super interesting what we can actually model with these equations. So I would argue, yeah, many scientific tasks boil down to kind of understanding the PDEs that govern a scientific system, and then solving tasks related to those PDEs. And I think one really important task that is done across many different fields is basically solving the differential equations. And what this really means is simulating systems. Like, given some initial condition of a scientific system, can we solve how it evolves in time, for example? And so this is an example of a really sophisticated simulation solving, well, a very coupled system, but mostly the Navier-Stokes equation, so fluid simulation of the output of a rocket engine. And we have many traditional methods for solving differential equations. You've probably heard of finite difference methods, finite element methods, finite volume, etc., etc. But the real issue with these methods is scaling them to large scale simulations, and that means their computational costs can be really, really expensive. So I mean, if you take this example, so this was a simulation run by NASA on a huge supercomputer, and it required over 500 million grid cells and ran for several weeks on 8,000 cores. So this is, supercomputing kind of scale simulation. And these types of simulations can cost upwards of 100,000 to $1 million to run per simulation. And so any way to kind of reduce the computational cost of these, and this is kind of where AI can come in potentially, would be very, very beneficial and would advance not just this kind of field of fluid simulation, but many other fields as well. I mean, there are also many other kind of what I would say is grand challenges of science where we can kind of use AI to help us solve these grand challenges. Simulation is one, but there are many others. For example, I was talking about AI for particle physics. So there I said that particle colliders generate huge amounts of data, and we just don't have enough time or humans available to interpret that data. So that's where AI can come in there, is to really just automate kind of the analysis of our experimental data. So this is a chart of the amount of data generated per month by CERN. So this is thousands of terabytes of data. I think AI can also help in these kind of scientific settings where it's the reverse is true, where we actually don't have very much data, and the data we have is very noisy. So this is an example of kind of exoplanets. So this is a way to detect planets orbiting stars, and this particular method looks for the planet to transit across the face of the star from our perspective. And what that does is cause a very small dip in the kind of sunlight that we receive from that star. And you can actually see it in the kind of flux if you look at the flux received as a function of time. Um, but the thing is that that dip in sunlight is very, very small. It's like less than 1% sometimes. And therefore the data that we have on these transits is very, very noisy. And it would be hard for me, I think, to look at this data and find a transit, but potentially an AI trained on this data could kind of see through the noise and be a better predictor of these exoplanets. And the final example would be on the right. There's kind of scientific problems that we're studying today are getting more and more complex. You can think of the evolution of the COVID virus is an extremely complicated kind of system, which is a function of global politics and transmission rates and lockdown measures and things like this. And so to kind of fully understand this system is very difficult. And AI might be able to help us kind of pull out different patterns and predict different things that we might not have seen as humans. Okay, so hopefully I've kind of showed you that AI does have an impact in science, and there are many challenges, big grand challenges that we need solving, and AI could help us solve. But what I also want to do is kind of bring it down to earth, and what I want to do is kind of motivate this field of scientific machine learning. And if we just use AI by itself, and really when we talk about AI, what we really mean is deep learning. I think the vast majority of kind of machine learning research today is concerned with deep learning. And if we just use deep learning by itself, we come up with many kind of challenges or limitations of these models. We see them in just standard machine learning tasks, but we also see them when we apply them to scientific tasks. And so I'm just going to list a couple, and these are really important to consider. So, I mean, the first is that just the sheer size of the models that we're training today in cutting edge AI. For example, if you take ChatGPT, and this was like one of the first versions, so not even the current version, they have hundreds of billions, if not trillions, of parameters in these models, and just dealing with that amount of data or that amount of model parameters is challenging in its own right. They also require a huge amount of data, and like I said, in some scientific applications, we don't have very much data at all, and that can be a real challenge to kind of feed these models. I think another issue is the kind of black box or lack of interpretability of these deep neural networks. This is a schematic of a ResNet, so a very famous kind of architecture. And it's actually really challenging to understand how the network kind of thinks or produces its outputs given its inputs. And there's obviously a lot of kind of interpretability. I mean, there's a whole field of explainable AI, and which is trying to come up with like justifications of the network's predictions. But it still remains challenging. Um, I think the other challenge is like to design the right architecture. We kind of really don't understand exactly what architecture to use. The kind of popular architectures have been evolving for a long time, from kind of fully connected to convolutional to ResNets to transformers, most recently. So th this is also a kind of a difficulty too. Um, I think one of the biggest problems with deep learning, which is most relevant to scientific applications, is the kind of issue of generalization. So this is kind of the well-known kind of limitation of deep neural networks, where you kind of they perform well on their training data sets, but when you test them on an out of distribution input, so basically an input that the network has never seen before, it kind of starts to break down and it's not able to generalize to a new task. Uh, this is kind of the real core thing that perhaps is limiting us to narrow AI systems instead of kind of artificial general intelligence at the moment. Um, I think coupled to this is the challenging of kind of reasoning. So we know by now large language models kind of hallucinate, and also image generation models also hallucinate, or maybe don't understand their kind of prompts that they're given from a kind of logical point of view. So for example, if you give DALL-E 3 like a prompt that says a street with absolutely no lampposts, all it does is generate streets with lampposts. And it's probably because the word lamppost is in the prompt. And so that kind of causes a large activation in the network somehow, and it doesn't really understand this kind of negation operator in the prompt. So, I mean, the point is that these limitations show up when you apply deep learning to scientific tasks, and that's a real problem. And so this is kind of one of the first pieces of research that I did, where I tried to apply in a very naive way kind of deep learning to seismic simulation. So you don't need to know much about seismic simulation. All the goal here is just to predict what the seismic waves or how the seismic waves propagate through the Earth when they start from some source. So this is kind of like an earthquake simulation, and uh, and the input to this kind of simulation is the structure of the Earth, or basically the velocity of the Earth. So this is kind of a 3D model. And then the output of the simulation is the amplitude of the seismic waves as a function of time. And what I did is I trained a very simple kind of encoder decoder convolutional network here. And I trained it on tens of thousands of example simulations with different Earth structures. And you can see that after training, if I test it with an Earth structure which was within its training data set, it gives a really good prediction of the seismic response. But if I give it kind of a velocity model, so in this case, I only trained it with these flat kind of horizontally layered velocity models. If I give it a velocity model that the network hadn't seen in training, so one that was curved, the prediction just really starts to perform really poorly. And this is just the poor generalization ability of the deep neural network just showing up in this scientific task. So I think what this does is motivate this field, which has really grown in the last, I would say, five years. Uh, it really motivates this field, which we call scientific machine learning. And so, what is this field like? How does it try to overcome these limitations of deep learning? Well, what I just told you is, if we just naively apply kind of a neural network to solve a scientific task, and we do it in this way where we just take, we have some inputs to our scientific task, we pass it to this kind of black box neural network, and we train the network to give some predictions. What I just told you, and what we always see is that these kind of this workflow suffers from those limitations, like the lack of interpretability. Uh, the networks can require a lot of training data where we might not have it, and they probably won't generalize well into new unseen inputs. And this kind of behavior doesn't really sit well with with scientists, because we what we really want is an explainable theory rather than a lack of interpretability. We want to be able to make kind of novel predictions with new training data, with new inputs, and to be able to generalize well and to design new experiments around those. And that's kind of, and what we have is kind of the exact opposite in this case. So the idea of SciML is really simple. It's to open up this black box and to, instead of using just an off-the-shelf deep neural network, what we do is we really think hard about how we design this kind of learnable system, and we insert our kind of scientific principles or prior scientific understanding directly into the machine learning algorithm to try and overcome those limitations. So this is the idea, to combine ML very tightly with existing scientific principles and understanding. And the kind of hypothesis or main belief of the field is that by doing so, we get more powerful, more robust, and kind of more interpretable hybrid SciML algorithms that can solve scientific tasks. And this field is actually really huge by now. And there's, what's really exciting is there's not just kind of one method for doing this. There is hundreds, if not many hundreds of methods that could be classed as SciML methods. And this is just a word cloud that I produced a few years ago, so this is certainly out of date by now. But you probably may have heard of some of these models like neural operators, physics-informed neural networks, which I'm going to talk about, neural differential equations, differentiable physics, the list goes on. There's so many kind of inspiring and creative models out there now in SciML. And yeah, this is just some more examples of how the field is growing. There's now been a SciML or physics-informed ML kind of workshop or component of in all the main kind of machine learning conferences by now. And then, I mean, this is just some data that I pulled off of Scopus. So this is kind of keywords, publications by keywords. And you can see all the kind of main keywords in SciML have been growing very quickly, if not exponentially, over the last few years. So the other thing I would note, especially to kind of the group today, which I believe are undergraduates and graduate students, is just the type of people that SciML train, and these people are really unique, and it's a really amazing skill set to try to acquire when you're working in SciML, because we don't just use machine learning, but we also have to have really good understanding of the scientific problems that we're trying to solve. And that often means SciML researchers are good at collaboration because we don't know everything, and we have to work with other people to get this domain expertise or machine learning expertise. It's also really important to have a good math foundation. As I said before, kind of scientific problems can be boiled down to studying PDEs at the simplest level, I guess. And high performance computing. I mean, a lot of the big scientific models like AlphaFold are trained on supercomputing centers and absorb a lot of data. And so being able to kind of have skills across all of these areas is really important in SciML. Okay, so I mean, by now you're probably wondering, how do we incorporate scientific principles into machine learning? That's kind of what I've been building up towards, and rather than replacing our existing workflows with kind of black box neural networks, how do we keep our workflows but put machine learning into them in where it matters? And so this is kind of what we teach on that whole course that I was mentioning at the start at ETH. And I'm obviously not going to be able to go through every SciML method here. In fact, I'm just going to focus on one. But before I do, I'll just give you a kind of high-level way of how I think about this. I generally see there as being kind of three main ways of kind of incorporating existing scientific principles into your machine learning algorithm. And I like to think of them as, firstly, through the loss function, secondly, through the kind of architecture of the neural network, and thirdly, through kind of what I would call hybrid approaches. So I'll just go through each of these. So in the loss function, what we do is we just kind of replace our whole existing workflow with a neural network. And the only place that we kind of insert our scientific understanding is specifically in the loss function. And we might say, as well as matching the kind of observational data using, a standard supervised loss, for example, what we would do additionally is to add some physics constraints to the network's output. So we might say, for example, energy is conserved, or some symmetry in the problem is obeyed, and that would be kind of a soft constraint. And this is probably the smallest way that you could put physics into the machine learning algorithm. A stronger way to put scientific constraints, or a hard way to put scientific constraints into your model, is to actually fundamentally change the architecture. And so this is where we can have things like rotationally invariant layers, or yeah, layers that conserve some other invariant property, for example. Now, the broadest category is what I would call hybrid approaches. And rather than kind of replacing the scientific workflow with a neural network, maybe that has a sophisticated loss or architecture, what we instead do is we keep our existing scientific workflow. So this could be something like, if I was trying to do simulation, our existing workflow would be like a finite difference simulation or algorithm. So we would keep that algorithm, and then we would put machine learning into a part of that algorithm where we really want to improve that algorithm. So you have these kind of hybrid approaches where we really truly blend these machine learning models with our existing scientific codes. And these are models such as neural differential equations, or more generally differentiable physics. And yeah, these can be very powerful, and you can be very creative in how you design these kind of hybrid methods. Another way to think of SciML methods is actually to think of them on a spectrum. This can be very useful. So what you can do is you can say, on the very left-hand side of the spectrum is our kind of black box neural networks that don't have any physics constraints. And then on the right, we can just say we have all of our traditional algorithms that don't use any kind of data-driven learning at all. So that would be like finite difference simulations, or inverse codes, or something like that. And then we can start to put, in a very kind of hand-wavy way, all these different SciML methods along this spectrum somehow. And you can, again, we're categorizing some of these by the loss function methods, the architecture methods, and the hybrid approaches. Now, this is useful because you can think of the kind of methods on the left-hand side as being fully learned. So they entirely rely on their training data to measure their performance. So fully data-driven, and have no kind of physics constraints apart from whatever the data kind of teaches the model. And then on the right-hand side, it's the opposite. So you have no learning, and therefore no data is required, and the physics is exactly how you've coded it in. And so SciML is really opening up this spectrum and saying, actually, we can start to learn, or make our kind of integrated workflow more flexible somehow. Okay. So I'm going to spend the rest of the lecture talking about one SciML method, but what I hope I've shown you is, or try to say, is that SciML is a much bigger field, and it's not just about this particular method. But so I am going to talk about physics-informed neural networks, which is one very, very popular scientific machine learning technique. And it's a technique which falls very strongly in this loss function category. So what physics-informed neural networks do is they train a neural network on some scientific data. I'll explain more in a minute. And they add this kind of sophisticated loss function that kind of makes the network obey physics. Okay. So let me describe exactly what a physics neural network is. So I talked before about the challenge of solving differential equations, or PDEs, and how it is extremely computationally expensive if we use a standard numerical method like finite difference or finite element methods typically. So what a physics-informed neural network is very simply a way to solve a differential equation. It's a new way of solving differential equations that is different to these traditional numerical methods. So I'm going to illustrate how PINs, so physics-informed neural networks, solve differential equations through this very simple ordinary differential equation. So this is an equation that is an ordinary differential equation. So just u as a function of t. And the specific equation is a damped harmonic oscillator. So this describes the kind of displacement of a mass on a spring as a function of time. So I think this is a canonical equation studied by many physicists, so hopefully this is familiar to a lot of people. And we have this second order ordinary differential equation. And we have u here is the displacement of the oscillator as a function of time, t. Then we have m, which is the mass of the oscillator, mu is the coefficient of friction, and then k is the spring constant. So these are kind of the physical coefficients that determine the kind of frequency and decay of the solution. And so we know that when we solve differential equations, we have to specify their initial conditions so that we can get a unique solution. And so here I've just said that the displacement of the oscillator starts at time equals 0, starts at 1, so it starts at the very top. And the velocity at time equals 0 starts at 0, so it starts from an initial stationary position. And so this is the solution. We know the analytical solution in this case is a very simple differential equation to solve. Okay, so how are we going to solve this with a neural network? Well, the idea is super simple. We just take any neural network. Typically, we use fully connected neural networks. So this is probably the most basic architecture there is. And what we do is we say that there is, in this case, a single input to the neural network, which is the time coordinate, t. We pass that through the network, and then we say that the network outputs, again, another single value, a scalar value in this case, which we say it just approximates the displacement. So what the neural network is really doing here is just directly approximating the displacement of the oscillator through time. Now, I think it's really useful to think of neural networks as basically just function fitting. This is kind of what we describe in our course is you can just think of the neural network as simply just a mathematical function that has some free parameters theta. And we kind of, the training process of the neural network is simply to choose or tune these parameters so that the function that the network learns approximates whichever function you actually want to learn. So when we train this pin, we're going to have to change these weights so that somehow the network ends up approximating this curve here. So this is u as a function of t. I hope that makes sense. If you have any questions on that, just let me know in the chat. That's a really important kind of concept to get for the rest of the lecture. Yeah, there's a question. There's a hand up there, I see. Mac.
Okay, so in this very simple case, what is the advantage of directly like using an analytic solution compared to using a neural network? Would this be a good use case of using a neural network to simulate that?
Yeah, actually, so I'm going to be talking about the kind of challenges of pins or the limitations or when you would actually use them later. So that's a really good question. And that's a lot, there's been a lot of discussion in the latest research on pins about when exactly we should be using them. So if you don't mind, I'm going to defer that until I get to that slide. But yeah, that's a really good question.
Thanks.
Okay, so I'll continue. So just to recap, we're using a neural network to directly approximate the solution, and we're going to try and tune the weights to kind of match the analytical or the true solution. So what we do is we train the network with this loss function, and this is kind of where the magic, if you like, happens. And what we say is that first we have two terms in our loss function. The first term we call a boundary loss. And so what we do in this term is we say, well, at time equals 0, we had these initial conditions where the oscillator should start at 1 and have a velocity of 0. So we assert that in the boundary loss. We say at the first term here, the neural network at t equals 0 should be close to 1. So this residual should be 0 if we're going to try and minimize the loss here. Similarly, we should say that the gradient of the network with respect to time, so this is the velocity of the oscillator, should be close to 0. And again, we're minimizing this residual in the loss function. So that's the first term we use in this loss function. The second or the most important term in the loss function is what we call the physics loss. It's also known as the kind of PDE residual. And what we do here is we say, well, we sample many coordinates, these green points in the domain, and we say that at every single point or every single coordinate, what we do is we evaluate this equation or the underlying PDE itself. So we say if we collect all of these derivatives of the network solution and sum them together in the way that the underlying ODE sums them together, that should equal 0 because that's what the underlying differential equation is telling us. If this collection of the gradients of the network and its value, when they're added together with these coefficients, they should equal 0. And that should be true for every single time point in the domain. And so that's what this physics loss is doing. It's really trying to say everywhere in the solution domain, the underlying differential equation should be obeyed. And so together, these two terms, these boundary loss terms and the physics loss, allow us to train a neural network to kind of fit this solution. And you can see the kind of prediction of this neural network as it trains with these two loss terms. So it's pretty cool. It's clearly managing to solve this harmonic oscillator problem, and it's only solving it with knowledge of what the boundary condition is and what the underlying differential equation is. We're not giving the network in its loss function any examples of the solution apart from the kind of boundary condition. So this is kind of quite different to how we would traditionally train neural networks, where usually we would have a supervised loss of the solution over many points, for example. So you can kind of think of pins as maybe an unsupervised method or very nearly unsupervised. I hope that's clear. If there's any questions, please let me know, because again, that's really important to understand how we train these. But yeah,
I think we're good so far. I think we're good so far.
Okay. Yeah, so this is obviously a scientific machine learning technique because we're adding our physics understanding in this physics loss. We're basically saying the differential equation should be obeyed. Okay. So this is a bit more practical help if you actually want to try and implement a pin yourself. This is actually what you would do if you're like a pseudocode, if you like. We would basically just we'd start with the differential equation that we want to solve. Then we sample our kind of points on the boundary that we know we have to obey, and all these what we call physics loss training locations, these green points. Then we compute the network outputs. We also compute the gradient of the network output with respect to its input, whichever gradients are required for evaluating these boundary terms and the physics loss terms. And then we collect all of these gradients and solution values together and sum them in the way that we create the final loss value. And then we have to do another computation this time with the gradient with respect the loss function with respect to the parameters of the network, so dl by d theta here, so that we can use gradient descent to train the network. And so we train these networks just like we train standard networks with, say, an Adam optimizer or something similar. Now, you might be wondering, well, how exactly do we get these gradients of the network with respect to its input and also the gradient of loss with respect to theta? Well, what's really cool and really what is the key enabler of making pins work is actually that autograd comes to rescue us, and we can compute all of these gradients just with backpropagation without having to define them kind of by hand, and we can do so fairly efficiently too. So yeah, we use autograd once to get dn by dt when we're computing these terms in the loss function. And then we use autograd on autograd again to get the dl by d theta once we've computed the loss value. So yeah, it's really interesting to understand how to do autograd twice, but I'm not going to go into that in detail, but I can point you towards our course material on that if you're interested. Okay. So I showed pins in 1D, so just u as a function of t, but obviously we want to simulate 2D systems, 3D systems, high dimensional systems as well in many scientific tasks. And what's great is pins can be very naturally extended to kind of higher dimensions or yeah, more complex problems. And so what I'm showing here is an example of using a pin. Now, instead of solving the harmonic oscillator, now we're going to solve the wave equation. We're going to solve it in 2D plus the time dimension. So this is kind of 3D overall. And so this is an example of, again, an earthquake simulation, similar to what I showed very at the very start of the presentation. And what we have is like a source here, a seismic source, and it's propagating through this Earth model here, which has just horizontal layers for simplicity. And this is the kind of ground truth finite difference simulation. And you can see the simulation propagating outwards. And actually a lot of kind of exciting kind of wave physics happens in this model. You get kind of compression of the wavefront as it goes to lower velocity regions. You also get reflections at every interface, velocity interface. So really exciting to kind of study from a physics point of view, and probably quite difficult to simulate from a physics informed neural network perspective. So the way that we set up the pin is very similar. The big difference here is that the neural network, instead of just having time as the input, it now needs to have two extra inputs, the X and the Y location in the domain. So yeah, we're now doing a 3D problem rather than a 1D problem. But the output of the network remains the same because the solution of this differential equation, the wave equation, in the acoustic case is a scalar value. It's the acoustic pressure. And we train the pin with a loss function that has two terms, just as I described before. So the first term is this boundary loss. And so in this case, in this paper that we wrote, we used a finite difference simulation for a very small number of time steps, basically just this red box here, to say what the starting velocity, the starting wave field should be, and we just matched the network's prediction to that. And then the physics loss again is going to sample many coordinates throughout the entire computational domain, so not just the first frame, but points all over the computational domain. And now the differential equation that we're going to assert is the wave equation. So this is now very different from that damped harmonic oscillator equation. And you can see we've got partial derivatives here. So this is now a PDE. But what's amazing is we can still use autograd in the same way that we did before to get these partial derivatives. It can still be done and still be done fairly efficiently with the autograd too. Okay, so what does it look like when we train this? Well, what we found, which was great, is that the pin does train in this setting, and we can get an accurate solution of these earthquakes propagating through the Earth model. The pin doesn't just get the general kind of outwards motion of the wave field, but it also predicts these interface reflections and the compression of the wave field, as I was talking about. And I can compare that to this, what I call a naive pin. So this is training a neural network without the physics loss, basically with only that finite difference data from the first time step. And you can see, I mean, it's fairly obvious that the network wouldn't learn the wave physics, but it does kind of get the general idea of the wave field moving outwards, but nothing more. So yeah, you can see really the benefit of adding this kind of physics loss into the loss function as we start to really nail the kind of physics that's happening in the solution. So I mean, if you're interested, here's some of the kind of hyperparameter specifics. So we used mini batches of physics loss training points in the loss function. So this is 500 random points every training step. And the network is fairly large. It has 10 layers and 1,000 hidden units. So, I mean, not a massive neural network by any means, but not super small either. We also used a soft plus activation. So you might be asking, why didn't we use a ReLU, a rectified linear unit? Well, there's a subtlety here that when you train the neural network here, when you're evaluating the loss function, you need derivatives of the network or second order derivatives with respect to its inputs. And if you think about a ReLU activation, those derivatives are always going to be zero because a ReLU activation is piecewise linear. And so it actually turns out neural networks with ReLU activations can't model the wave equation because they don't have continuous second order derivatives. So that's kind of an interesting thing you have to remember with pins is you have to use kind of continuously differentiable activation functions inside the architecture. And then we use the standard kind of Atom optimizer to solve. So promising, at least, that pins can kind of solve these maybe more complex, high-dimensional simulation tasks. What I find more exciting about pins is that they can be extended to inverse problems. So what is an inverse problem? An inverse problem is where you don't just want to simulate or solve this for the solution of the differential equation, but you actually want to solve for like an underlying parameter of the equation that maybe you don't know, that you haven't got observations of. So we can imagine like this situation where, well, we call this non-destructive testing. It's where you can imagine this box now is a plate, for example, and there's a crack somewhere in this plate. And the way that we can we don't know where that crack is, but we can try and infer it by vibrating the plate and measuring the vibrations or the displacement of the plate, and then trying to reverse engineer where the crack might create those vibrations from. So this is exactly what's happening here, is measurements of this displacement of the plate, and you can see some kind of interesting things happening around here, and you might think that there might be a crack around this region, for example. So what we're going to try and do is, given all of these observations of the displacement here, so this, I'm calling it U data here, we're going to train this neural network to match that data. So now this isn't just a boundary condition. This is like learning basically measurements of the solution all over the domain. We're going to train the pin to reconstruct that, but we're also going to train the pin to match the wave equation, because we know these waves obey the wave equation. And now the thing that we don't know, the underlying parameter that we're going to try and learn, is the wave speed. So basically the speed of the all over the plate, what that wave speed looks like. And the idea is that the crack should show up in this wave model as a kind of perturbation, if we can learn a good wave model. So that's the kind of trick here, is that if we don't know what one of these underlying parameters in the equation is, we can replace it with another neural network that learns that underlying parameter at the same time as the neural network is training. So when we train the network, we don't just optimize the weights of the network, we also optimize the weights of this kind of unknown parameter or unknown network parameter as well. So here, whenever we need to query the kind of wave speed in this loss, and we don't know the wave speed, we use a neural network here, which takes in the X and Y coordinate here, and then tries to predict what the wave speed is. And the kind of magic of this is that as the pin trains, it not only learns like the correct solution, this is the prediction of the pin here, predicting the displacement of the plate. But also, after you've trained it, should be able to learn the velocity too. And yeah, this is actually what happens, and this is the prediction of that velocity network after the pin's been trained. And we're querying that network over all XY points, and you can see that it's learned basically a constant velocity, but it has learned exactly where this crack is, or the perturbation in the velocity model. So I think this is really, really nice, because basically pins can kind of seamlessly solve these kind of messy problems where you understand what the physics is, but you also have some data, and you might want to learn something about the physics on top. And I think there's been a lot of great research beyond this paper that has really shown the power of pins. So coming back to that question about where you would maybe use pins, I think this is a really good place to think about using them.
Okay. Before we move on, we have one question from the chat from Yunji. Do
Yep.
we sum the boundary loss and the physics loss to make one pin?
Say that again. Do we
add the boundary loss and physics loss to have one physics-informed neural network in
Yeah,
them?
let me go back to this. So we have, say, when we're solving this equation, we have just one neural network. So the network takes in the time coordinate and outputs the prediction of the solution of the equation, in this case, the displacement. And then we train the network with a single loss function, but the loss function has two terms. So we add together this boundary loss and the physics loss. And when we train the pin, we backpropagate, or we get gradients of the loss with respect to the parameters and backpropagate through it to do gradient descent. I hope that makes sense. And maybe if you were asking about this specific example, we also do this. We do the same, but in this case, we have two neural networks. So one is predicting the solution, and one is predicting the velocity model, and they're both trained at the same time. So when we backpropagate through the loss function, we update the weights of the network and phi, and again, autograd can let us get both those gradients in parallel.
Sounds good. Let's move on.
Okay, good. Right. So yeah, so I've been hinting, well, the initial PIN paper came out in 2017. Actually, the very first research on pins, as far as I know, started in the 1990s with some very simple implementations, but this kind of key idea of adding physics to the kind of loss function. But yeah, since the kind of seminal paper by Ricey in 2017, the amount of pin-related publications has just been growing rapidly every year, and I think last year was over. This is just a couple of keywords, but I think it's much more than just 1,000 related pin papers. So it's become a huge research field in its own right. And if you're really interested in the kind of state of the art in pins, I think this review paper that came out a couple of years ago already, but it's still a really good kind of summary of the state of the art in the field, I would say. So yeah, let's go into that question that I asked that audience member asked in a bit more detail, and when should we use pins to replace our existing numerical methods, our finite difference solvers, our finite element solvers? And so to answer that question, you should really understand what the advantages and kind of limitations of pins are. So let me just talk about the advantages first. I mean, first, you might realize that a pin is basically a mesh-free way of solving differential equations. At no point have I talked about like a computational mesh or a finite difference approximation. Uh, we're just using a neural network, which is a continuous kind of approximation of the solution, and we're training it with these kind of randomly sampled co-location points. So that can be really useful. Sometimes in industry, when we're using FEM, we can spend a long time just designing an appropriate mesh. For example, that rocket simulation, you have to have a really good mesh that is really fine, at the edges of the rocket and maybe coarser elsewhere. But to design that takes a very long time. Also, they can solve these forward and inverse problems seamlessly. So that situation that I told you about, which is kind of a messy problem where you have some data and maybe not quite a full understanding of the physics. And there's been some research that has shown they can perform quite accurately for high dimensional problems compared to finite difference methods or finite element methods, which don't generally scale as well to high dimensions. So I would say these are probably the advantages, but there are some big limitations, and that's what I'm going to focus on kind of for the rest of the talk. Basically, they can be very expensive to train, and they're not guaranteed to even converge on the solution. In this case, it is converging, but the loss function is actually very complicated, and there's no guarantee that gradient descent or Adam would actually give you a good answer. And they can be challenging to scale to high frequency problems. So I mean, the caveat is that I just said that there's thousands of pin researchers and papers out there, and there's been a lot of techniques that have tried to overcome these limitations. So I'm just going to talk about one, and this is kind of scaling pins to high frequencies. And I'll see how far I get. I'm conscious of time, but Calvin, I guess I maybe have 10 more minutes or so.
You can go on for however you feel, but I understand it's a bit late for you right now.
Yeah, no, that's okay. Yeah. So yeah, so the goal is well, so let's go back to this harmonic oscillator example, and I picked actually a very nice example where the solution was very low frequency and it does converge within a few thousand training steps. But the issue is that if I increase the frequency of the solution, so basically add more cycles to the solution, so change the kind of physics parameters so that it's higher frequency, the pin all of a sudden really starts to struggle to kind of scale. And you can see it takes kind of tens of thousands of training steps and doesn't even manage to kind of model the first cycle of the solution. And this is a really big problem with pins actually. And you can see if we want to scale to like a high frequency simulation that it's not going to work. And so you can ask the question why. So one of the big reasons why kind of pins struggle to scale to high frequencies is this issue which is known as spectral bias. So this is a well-studied and well-known kind of effect of neural networks, which is that they typically tend to learn high frequencies much slower than they learn low frequencies in their data that they're trained on. So this is an example of a neural network, fully connected network, fitting a multi-scale function. So it's got multiple frequencies in this function. And you can see as the network trains, so this is a standard supervised network. No, there's no pin here. As it trains, it learns the kind of low frequencies of the solution and eventually starts to fill in the high frequencies. And we can actually study this under a field known as neural tangent kernel theory, and kind of prove like convergence rates. But you can see how this can be is a really bad kind of problem for PDEs, where we generally want to model like high frequency functions. So yeah, just to summarize, as we add higher frequencies, we have this issue of spectral bias, but we also need a larger neural network to kind of be more expressive to model all these cycles of the solution. And we also need more training points as well, kind of co-location points to kind of sufficiently sample the solution. So this all accumulates and kind of leads to a really difficult optimization problem that doesn't scale well with frequency. So that's what my group is really interested in is this general idea of taking SciML methods like pins, and instead of kind of staying on the left-hand side where we have these like small scale simulations, to really try and scale them to real world multi-physics multi-scale systems that actually have like a real world impact. And that's the kind of question that we're trying to answer with our research. Now, this is a really hard question to answer, but I think it's important just to ask the question anyway. So the method that we took was a very simple idea, and it was to combine pins with domain decomposition. So I mean, this is a very classical idea, and it's very simply to divide instead of using a single global neural network to model the whole solution. Why don't we take our kind of computational modeling domain and divide it into many subdomains, and then have a separate neural network in each subdomain to model the solution locally? And the kind of hypothesis is that the kind of resulting local optimization problems, which are coupled, are easier to solve than the kind of one big global optimization for a standard pin. So this is a paper that was one of the first to propose combining domain decomposition with pins. But what I'm going to tell you is a different technique, which is our method. And what we did is we divided the domain into many subdomains, but we said that these subdomains are overlapping. So you can see an example kind of rectangular domain decomposition here. And we went in and placed a single neural network in each of these subdomains. And then we did a couple of really important things. The first thing we did is remember the input to the pin is always the coordinates inside the domain. And so what we did is we normalized those coordinates in each subdomain network to the range of the subdomain, so that they within the subdomain they were roughly between -1 to 1. So we call this subdomain normalization. And what that really does is reduce the effect of spectral bias by making sure the network only sees inputs between kind of -1 and 1 rather than over a much larger domain. We also do some unnormalization to make sure the outputs are also between -1 and 1. And then the next important thing is we apply a window function, and this basically constrains the network to within its modeling domain, the subdomain that it's in. And what we say is the final solution of the differential equation, U here, is just a summation over all of these individual subdomains with the normalization applied and the window function constraining each subdomain network to its subdomain. So that's the idea, is to kind of use this kind of what you could think of as a more sophisticated neural network architecture. Really, it's just a lot of neural networks summed together rather than a single neural network to predict the solution. So this is just an example. We call these finite basis pins, FB pins. And this is an example in 1D just to help you. So this is the kind of final solution that the FB pin is modeling. But on the left-hand side here is just the example of each of these individual subdomains and their own solutions that are then summed together to produce the final prediction. And you can see here the window functions which are constraining the networks to their subdomains and the definition of the overlapping subdomains here. So yeah, like I said, you can think of FEPINs as simply a custom architecture. We're just kind of summing over multiple network heads rather than a single network. And actually, we train FP-pins with exactly the same loss function as pins. So, a boundary loss and a physics loss. And we just backpropagate through the whole summation and all of the networks together to update the weights. So it turns out FP-pins are much better on this 1D harmonic oscillator problem than pins. This is just a straightforward comparison of a standard pin with this summed FP-pin solution. And yeah, what we can see that the FE pin converges much quicker than the pin, manages to get all of the cycles within maybe 10,000 steps. And if you look at the kind of convergence curve on the bottom right here, where you can see the pin in red doesn't really converge at all, but the FE pin doesn't only get a much higher accuracy, but it actually does it in way less flops as well. So this is kind of floating point operations or kind of amount of computational resource to train the FE pin. And the reason it does it more efficiently is because we actually can get away with much smaller neural networks in each subdomain rather than having a large network with kind of deeper layers and more hidden units. So this is kind of a double win. We get higher accuracy and more efficiency at the same time. And so this is an example of really scaling FP pins up. So like I was saying, we really wanted to solve more larger scale simulations. And so now what we're doing is we're simulating the wave equation over a much more complicated velocity structure here. And you can see that the simulation initializes with a multi-scale sources. So we have like a high frequency source here and a low frequency source here. And I'm absolutely sure that a standard pin would not be able to simulate this at all. And the FP pin, we're using 60 by 60 by 60 subdomains. So this is over 200,000 individual neural networks all being trained together here. And the total number of parameters is nearly 9 million parameters, so a much larger model. So we think we're stepping towards improving pins and scaling them up to higher frequency problems. I think I'm going to leave it there. We're not done by any means. The big issue still is the training time. So even though I just told you that FE pins are kind of faster than pins, they're still slower than finite difference simulation. This FE pin took about 2 hours to train on the GPU, whereas the FE simulation takes maybe 5 minutes. So we're still not there, but we have many other ideas. And what I would have liked to told you is that we have now a way to train FE pins that's much faster. And it converts the training algorithm from a gradient descent algorithm into a linear solving algorithm. But I don't have time to talk about that today, unfortunately. But what I do want to do is just end with, I just want to end with my last few slides, which is some more opportunities to get more into SciML. If I've inspired you in this talk. So I'm going to be giving a workshop on finite basis pins in October in the Netherlands. This is open to anyone to apply. It's a summer school. So please have a look at that if you're interested in learning about state-of-the-art physics-informed neural networks and coding them yourself. Like I said, Calvin went on this course and we got some really great feedback from the students at ETH for our master's course. So we taught this last year and we also put it on YouTube, so you can follow this QR code and watch the lectures on YouTube for free. And we'll go into way more detail about all these different SciML methods. And then the final thing I want to mention is my lab at Imperial. So we don't just work on pins. We want to design these general scalable scientific machine learning algorithms and apply them to kind of infractal problems across different scientific domains. And so yeah, we're working on these kind of multi-scale simulations with pins, but we also do work across many other things. So we're looking at kind of geometry-informed neural networks. We're also looking at AI for quantum mechanics. And then we're applying SciML to things like planetary image denoising, climate modeling, as I was talking about at the start, and also modeling chemical reactions as well. So yeah, please reach out to me if you're interested in learning more. And thank you very much, Calvin, for having me.
Thank you very much for the talk, Ben. One question from the chat I have from Ian is that how did you define the finite domains in the finite basis pins exactly?
Yeah, this is a question I get asked all the time, and it's a very prudent question. So the question is, how do you define these subdomains? So the answer is not a very satisfactory answer. It's basically we handpick them, and it's this classic kind of chicken and egg situation, which I would also say we have in finite element methods, where we kind of have to pick the subdomain decomposition to match the solution frequency, but actually we don't know what the solution is. So yeah, I don't have a good answer, but what we are doing at the moment is looking into learning this domain decomposition. So instead of like assuming that we know what this is, we can actually kind of parameterize these window functions and have the network kind of adapt in a kind of mesh refinement or adaptive mesh refinement sort of way. So that's what we're thinking of.
I see. Okay, thank you. And one last question I have from Assad is like, is there any like specialized hardware like FPGAs you can use to train pins yet, or?
Yeah, good question. So I mean, we already have GPUs, and GPUs are absolutely fantastic at training neural networks. And honestly, with pins, we're not really doing much different. We're still training neural networks. So I think GPUs are probably the fastest. Maybe you could write a very specific FPGA algorithm for a particular architecture, and that could be accelerated. But where I think is challenging is using autograd to estimate gradients. And I said that it can be efficient, but actually when you have higher order gradients like du by dx to 3, like third order derivatives, autograd gets exponentially more expensive. And so I think any kind of way of improving the gradient computation would be good. And there's things like using finite difference approximations in pins to do that. I also think fundamentally changing the optimization algorithm instead of using gradient descent to something faster would be very, very helpful as well.
I see. Thank you very much.
Thank you.
Great. Thank you, everyone. And thanks again, Calvin, for having me.
Yeah, so thank you for having joining the lecture series. Thanks. I think you might have to email the recording me later because it's recorded on your end. So just email me whenever you have the time.
Yeah, if it saves to my computer, then I'll send you a copy. No problem.
Okay.
Yep.
All right.
Any other questions or?
Mac has a question.
Oh, after like checking like these opportunities, one thing that really catches on is the topic of quantum machine learning, which is something I have been focusing on a research project which I have started back in, I don't know whether it's like March or February, but it has to do with like medical applications and especially on the imaging and clinical data on pancreas cancer. So do you think this would also be like a relevant topic for scientific machine learning?
Yeah, SciML is such a broad field. I think that you could have anyone talk about any machine learning application to science, and it would be relevant.
Yeah.
I'm most, like I said, I'm most impressed by these methods that don't just replace your workflow with a neural network, but actually incorporate the network into the workflow in some way. So we're doing this in our quantum ML work actually. Well, yeah, I don't have a slide to really explain it, but what we have there is like an existing quantum theory, so like a mathematical theory, and we don't know some components of the theory. So there's particular kind of functions that we don't understand in this theory, and so we're kind of learning within the constraints of that theory to try and understand these unknown functions. So it's kind of like function discovery or theorem proving with a learnable component, things like this. So that there's so much creativity that you can do in kind of designing these hybrid methods.
Sure, I have been like taking these notes throughout, so I'm definitely sure like one day like what are the benefits right now, the measurable benefits of quantum computing? Because right now I have actually made a quantum machine learning project last summer on identifying weld defects, but unfortunately it has not demonstrated any
Yeah.
measurable like improvement over the classical convolutional network, and that was trained using a smaller convolutional network rather than the full model because I do not have cloud access. I'm running this locally on my own computing, and sometimes it just does not fit into the large model.
Yeah, I mean, so I'm definitely not an expert on quantum computing. So I think there's a difference between using AI to help quantum research and quantum computing there. And you also have quantum machine learning, like designing machine learning algorithms to run on quantum computers. So these are kind of all fields in their own right. But I mean,
So
yeah, go on.
sorry about that. So quantum machine learning is itself an own field, right?
Yeah, absolutely. Yep. Yeah, so you design machine learning models and training algorithms that the desire is that they run much faster on a quantum computer than they would do classically. But I think the issue with and again, I'm not an expert, but what I believe is uh, firstly that it's hard to come up with a design a quantum algorithm because these quantum computers evolve very differently to how traditional classical computers evolve, and also to deal with the kind of noise in the quantum computer and to deal with error correction. So, but obviously there's a lot of progress in designing better quantum computers and better error correction algorithms as well. So, yeah. Okay, so I think I probably have to leave now.
Okay.
But
Okay.
thank you very much.
Thank you. Let's end the meeting.